projects. In this video, we will explain about the project, which is PoxNet22, a fine-tuned model for the classification of monkeypox disease using transfer learning. Introduction of the project. Public health experts are currently facing a dual challenge with the ongoing global COVID-19 epidemic and the emergence of new monkeypox outbreak. Monkeypox and orthopox virus share similarities with variola, cowpox, and vaccinia. The current outbreak has a significant impact, particularly in Central and West Africa. The Massachusetts Department of Public Health Laboratory Response Network confirmed the presence of monkeypox in a Massachusetts resident using real-time PCR on lesion swabs. The virus belonging to the Western African subclad has rapidly spread within the United States with 17 confirmed cases by the end of the May and total over 48,000 cases globally within 4 months, resulting in 13 fatalities. In response to the monkeypox outbreak, the United States initiated a randomized controlled trial to assess the effectiveness and safety of tecovirimat as a potential therapy. The Centers for Disease Control and Prevention and the Food and Drug Administration expedited and extended access strategy while awaiting RCT results, emphasizing the urgency in addressing the hazards of monkeypox. Acknowledging the potential of machine learning with the artificial intelligence, the project highlights the role of ML in various applications, including medical imaging and disease detection. Specifically, it refers to a study proposing layered ensemble meta-classifiers and feature fusion for large-scale COVID-19 classification, showcasing the capability of ML in enhancing diagnostic accuracy. Given the limited existing research on usage using image processing and machine learning for monkeypox diagnosis, the project aims to fill this gap. The project outlines its methodology, including data pre-processing, augmentation, and the application of different models. The proposed PoxNet22 model, fine-tuned from Inception v3, is introduced as a potential solution to classify monkeypox more precisely, emphasizing its potential implications in improving the accuracy of monkeypox diagnosis through advanced technology. Objective of the project. The primary objective of the project is to leverage deep learning and image processing methods to develop a model that can facilitate early and accurate diagnosis of the monkeypox. The urgency stems from the potential for rapid disease transmission, especially within specific demographics, and the need for swift identification to prevent further spread. The project aims to harness the capabilities of deep learning technology to enhance the diagnostic process for monkeypox by integrating advanced computational methods. The goal is to expedite the identification of monkeypox cases, considering the critical need for prompt intervention during outbreaks. Given the challenges posed by simultaneous occurrence of a monkeypox outbreak and the ongoing COVID-19 epidemic, the project seeks to address the diagnostic challenges effectively. This includes developing a model that can distinguish monkeypox from the other illness with similar symptoms and epidemiological context. The project incorporates data augmentation techniques to enhance the quality of the dataset and mitigate the risk of overfitting. Furthermore, the objective involves applying a transfer learning strategy to evaluate the performance of different deep learning models and selecting one with the best precision, recall, and accuracy metrics. The ultimate objective is to propose an effective model naming PoxNet 2022 by fine-tuning the best performing model. PoxNet 22 is designed to achieve high accuracy, precision recall in classifying monkeypox. The outcomes of the project aim to provide valuable insights for clinicians, aiding them in accurate classification and diagnosis of monkeypox classes, ultimately contributing to the effective public health management. To implement this project, we need software and hardware requirements. Software requirements are application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. And the hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement the project, we have designed various steps in the flow of work. The first step is importing the packages. In this essential step, we import necessary Python packages and libraries that are required for the project. We imported NumPy and Pandas for data manipulation, Matplotlib for visualization, TensorFlow and Keras for deep learning, Flask for web development. Coming to exploring the dataset, here we analyze the dataset, which is monkeypox. It is categorized into two groups, which is monkeypox with argument and without argument. Coming to argument, augmentation refers to the application where transformations to the existing dataset to create new instances of the data. In the context of image data, Augmentation involves making slight modifications to the original images in the training dataset. The purpose of the augmentation is to artificially increase the diversity of the training data, which in turn can improve the performance and generalization of the deep learning models. So, in this with augment, we have the images with additional augmented variations for the diversity. Coming to without augment, here we have original images without the augmentation. We utilize the image dataset, which is monkeypox dataset from the RoboFlow for monkeypox detection. The next step is image processing with the image data generator. This step involves utilizing image data generator to augment the dataset through several transformations. And the transformations are rescaling the image, which is adjusting image intensity values. Shear transformation is changing the shape of the images. Zooming is altering image scale. Creating mirror images, which is horizontal flip. Adjusting image dimensions, which is reshaping. The next step is image processing with torch vision for detection. This step involves applying additional image processing using torch vision, a library for computer vision tasks. Specific enhancements and the transformations will be performed for tailored of the detection task. Coming to building the model, this step involves defining the architecture of the deep learning models both for classification and detection. It includes defining the layers, specifying connections, and configuring parameters to enable the model to learn from the provided dataset. We build all the models for the augmented data and without augmented data. The next step is training the model. This step involves using the prepared dataset to train the model. During this process, the model learns to recognize patterns and relationships within the images, gradually improving its ability to make accurate predictions. Flask framework with SQLite for sign up and sign in. This step involves implementing a web framework along with the database SQLite to manage user authentication. It enables users to sign up and sign in, providing a secure and personalized experience. The next step is user upload image for analysis. This step involves allowing users to upload images for analysis. It facilitates user interaction with the system, enabling them to submit images that they want the model to analyze. The next step is the given input is pre-processed. This step involves preparing the user uploaded image for the model input. It involves resizing, normalizing, and applying other transformations to ensure the compatibility with the model's expectations. Using trained model for the prediction. This step involves applying the trained model to predict the outcome based on the pre-processed user uploaded image. The model leverages the knowledge gained during the training phase to make predictions. The last step is final outcome is displayed, displaying the final predictions, which are the results to the user through the web interface, indicating whether the uploaded image contains monkeypox or not. Algorithms which are used in the project are ResNet50. It is a deep convolutional neural network architecture that consists of 50 layers. It is part of the ResNet family, known for its use of residual connections. Residual connections help mitigate the vanishing gradient problem, allowing for training of very deep networks. ResNet50 is employed for its ability to handle deep architectures effectively. VGG16 is a convolutional neural network architecture with 16 layers developed by Visual Geometry Group, which is VGG, at the University of Oxford. It is characterized by its simplicity using small convolutional filters with a fixed size of 3 by 3. It is chosen for its simplicity and effectiveness, and it is often used as a baseline architecture for the image classification tasks. The next model is Inception ResNet V2. It is an extension of the Inception architecture with the incorporation of residual connections. It combines the ideas of Inception module for feature extraction and residual connections for ease of optimization. It is selected for its powerful feature extraction capabilities. The combination of Inception and residual connections will provide high quality features for monkeypox detection. The next algorithm is DenseNet201. It is densely connected convolutional neural network architecture. It introduces the concept of dense blocks where each layer receives direct input from all preceding layers in the block. This promotes feature reuse and reduces the number of parameters. It is chosen for its parameter efficiency and feature reuse, potentially providing a robust feature representation for the monkeypox detection. The next model is Inception V3. It is an improved version of the original Inception architecture. It introduces factorized convolutions and incorporates batch normalization. It is designed for efficient use of computational resources. It is used for its balance between computational efficiency and performance. It is suitable for the applications where resources are in consideration. The next algorithm is EfficientNet B7. It is part of the EfficientNet family, which scales network depth, width, and resolution with a set of compound scaling coefficients. EfficientNet architectures are known for achieving high accuracy with fewer parameters compared to traditional models. It is chosen for its efficiency in terms of parameter usage and computational cost. The next algorithm is PoxNet, modified version of Inception v3. PoxNet is a customized model based on modifying the fine-tuned version of Inception v3 architecture. It is designed to address specific requirements and the challenges posed by monkeypox detection task. The modifications aim at improving precision, recall, and accuracy for this particular application. We built all these models for augmented data and without augmented data. As an extension, we further enhance the performance by exploring other YOLO techniques, which are the YOLO family for the detection of disease. Also, as an extension, we built the front end using Flash framework for user testing with the user authentication. We have used accuracy, precision, recall, and FN score, which are the performance metrics to evaluate all the classification models of the project. Classification is a machine learning task where the goal is to assign predefined labels to the input data based on its features. For example, in image classification, the model learns to categorize images into specific classes such as recognizing whether an image contains a cat or a dog. We have built all the classification models for the augmented data and the original data. So here we have performance comparison graphs for the augmented data. This is accuracy comparison graph, where on x-axis represents accuracy score for each algorithm, and on y-axis we have algorithm names. Accuracy measures the overall correctness of the model by calculating the ratio of correctly predicted instances to the total instances. This is precision score comparison graph, where on x-axis represents precision score for each algorithm, and on y-axis we have algorithm names. Similarly, we will have for other graphs also. Precision evaluates the accuracy of positive predictions made by the model. It is the ratio of correctly predicted positive instances to the total instances predicted as positive. This is recall score comparison graph. Recall is also known as sensitivity or true positive rate. It measures the ability of the model to capture all positive instances. It is the ratio of correctly predicted positive observations, which is instances, to the total actual positive instances. This is FN score comparison graph. It is the harmonic mean of precision and recall. It provides a balance between precision and recall, and it is particularly useful when there is an imbalance in the class distribution. Here we have performance comparison graphs for the original data, which is without augmented data. This is accuracy score comparison graph, precision comparison graph, recall, and FN score. We have used precision, recall, and map, which are the performance metrics for evaluating the detection models. Detection, which is object detection, involves identifying and locating multiple objects within an image or the video, providing both categorization and spatial information. It goes beyond classification by outlining the position of the objects with bounding boxes, commonly used in applications like image-based security systems or autonomous vehicles. So here we have performance comparison graphs for the detection models. This is precision score comparison graph. This is MAP, which is mean average precision. It is a popular metric for the object detection that considers both precision and recall at different IOU, which is intersection over union thresholds. It averages precision values across different IOU thresholds and computes the mean. This is recall score comparison graph. The algorithm which performs well among all these metrics will be used for final detection. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the dataset folder in which we have augmented data and the original datasets. We use both the datasets for training the algorithms. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. And these two are the model files, which contain the algorithm information and that will be loaded into the project code during runtime. This is the sign-up file. This file is a database file used to store the user information. And these are the two IPYNB files. These files are the Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. By this, current directory will change to the code folder's path. Here we need to type the command python space app.py and then click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the localhost and port, unless configured differently. This is the localhost and this 5000 is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project, which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a login link. First, we need to click on that. Here we need to enter all the sign up details if we are signing up newly. I have already signed up and have an account in it, so we'll directly sign in. For that, click on sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password. Now we need to click on sign in. We have signed in successfully and we are redirected to prediction page. Now we will do the classification and detection of monkeypox disease. First, we will do the classification. For that, under prediction, click on classification. Here we can see a choose file button. We need to click on that for uploading the images. So I'm clicking on choose file button. From the folder, I'm selecting the first image. Now click on open. And here we can see that image has been loaded. Now click on upload. Based on the uploaded image, the application has predicted as patient is diagnosed with monkeypox, which means patient is affected with monkeypox. Now we will try giving the other image. Click on try again. Click on choose file. I'm selecting this image. Click on open. Now click on upload. Here, based on the uploaded image, the application has predicted patient is diagnosed with monkeypox. Now we will give the other image. Click on try again. Click on choose file. I'm selecting this image. Click on open and now click on upload. So here we got the prediction as the patient is diagnosed with the other disease, which means person is not having monkeypox disease but is having some other disease. Now we will be doing the detection of monkeypox disease. For that, under prediction, click on detection. Similar to classification, here also we have choose file button. We need to click on that for uploading the disease images. Now I'm selecting this image. Click on open and now click on upload. Here we can see that application has detected the disease and it has drawn bounding box around the disease and it has labeled it as monkeypox with the probability score. Now we will try giving the other image. Click on back arrow. Click on choose file. Now we will upload this image. Click on open and now click on upload. Here we can see that application has detected the disease and it has drawn bounding box around it and it has classified as others, which means it is not monkeypox disease but it is some other disease and it has given a probability score for that. Now click on back arrow. Click on log out. In this way, if we upload the images to the system, then the system will detect the disease. Conclusion of the project. The project successfully demonstrates the effectiveness of machine learning by employing a variety of state-of-the-art algorithms such as ResNet50, BGG16, Inception ResNet V2, TenseNet 201, Inception V3, EfficientNet B7, and a custom model which is PoxNet22 for accurate and reliable monkeypox diagnosis. Through extensive dataset augmentation techniques including rotation, flipping, zooming, and other transformations, the project ensures that the machine learning model are trained on diverse set of images. This augmentation contributes to improved model generalization, enabling robust performance on varied monkeypox scenarios. The integration of Flask framework with SQLite for user sign-up and sign-in provides a user-friendly web interface. Users can upload images for analysis, facilitating broader community involvement and accessibility to the developed monkeypox diagnosis model. Public health professionals, clinicians, and patients will be benefited from the project by gaining a powerful tool for a swift, accurate, and monkeypox diagnosis, leading to improved outbreak management and enhanced patient outcomes.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.